to model T as a function of theta ue x due dx. Oh, and also nu, right? There are a lot of parameters you need to extrapolate. So for all our interest, we want to reduce the set of parameters to as much as possible. And using physics, especially dimensionality analysis, is an excellent way for us to be able to do that. So here, let's say we have theta has a length scale, UE has a L over T scale, length scale, due dx has a 1 over T scale, and the nu has a, what is it? It's L squared over T scale, right? So let's figure out a few non-dimensional parameters. Theta over x is 1, right? Okay, so theta over x, they are both L, no problem. Okay, and UE, due dx, and theta, if you combine them, you get 1. So, to do is you can take due dx and you divide by UE, so that we are gonna get a 1 over length scale, okay, and you multiply, for example, by theta, right? So that's another non-dimensional parameter. The last non-dimensional parameter is something that involves nu. So you take nu, and I still want to have a due dx. So that's 1 over T. I divide by nu to get a 1 over length squared, and I have a theta squared, right? So I only have L and T inside all these parameters, so I can reduce it by 2. So T turns out can, in principle, be modeled as a function of all these 3 parameters. So now is the time to use physical arguments to see which of them make sense. Theta over x, should it be involved in modeling how much the skin friction coefficient is? Think about this. So theta over x, so this is basically if I have a boundary layer, right? So maybe this is stagnation point. X is like how long I have traveled in the streamwise direction, and theta is like the momentum thickness. Is the ratio predictive of what family? So if there exist self-similar solutions, right, then theta over x is changing while the family is not changing. So at least I can say that theta over x by itself should not be able to determine which family to choose from. And that is true for all other Faulkner-Scan families. Like theta over x is going to be changing while the boundary layer profile remains similar, right? Okay, so theta over x alone cannot determine what t is, right? Or any other quantity that determines which boundary layer profile we are choosing from the Faulkner-Scan family. How about this one? How about theta over UE times due dx boundary layer? So if we have that, does that allow me to choose anything other than the Blasius boundary layer profile? So we just said for Blasius, we have the condition right? It's just the one. So what we are doing is that from these 3 parameters, we want to choose which one is going to uniquely identify one member of the Blasius, of the Faulkner-Scan boundary layer profile. Which of these is x? Right, at a certain combination of theta over x, theta over UE times due dx, and theta squared over nu times due dx. For the third one, you are saying?
Yeah.
So for the third one, um, you said it works for Blasius because
du
dEdx is 0, and it works for the stagnation point flow because
it'll be constant and data is also du dx.
right. So you have chosen two representative cases that kind of says that the third one seems to be working, right? While the previous two ones, neither one works for both cases, right? The first one falls apart even for Blasius boundary layer because theta over x changes. And the second one, it's constant for Blasius boundary layer but falls apart for stagnation point flow because theta is constant and UE increases proportionally, right? So, okay, and the third one seems to be right for both cases, and we can actually show that it is a constant for every member of the Blasius boundary layer. Okay, so that is true because du dx is, so what is du dx? du dx is basically here. du dx is my alpha prime, which is unique for every Faulkner-Scan family member, right? So du dx is alpha prime divided by x times ue, and I multiply this by theta squared over nu. All right. And so if you go back to the Faulkner-Scan derivation of the Faulkner-Scan family, we actually took nu. We actually had something called the nu times x divided by ue delta square in front of the f triple prime term. And we set the delta so that this term is equal to 1. Okay. That means if I look at these three combination of these three terms, it is actually alpha prime times theta square over delta square. So that's what it is. So for every alpha prime, we can solve the Faulkner-Scan equation. We can compute the theta, the momentum thickness, in the eta coordinate. Okay, and in the eta coordinate, delta is equal to 1, right? So basically, this is alpha prime times the theta square in the eta coordinate.